Yeah, we probably should begin. Today wouldn't take long because it would be, well, wouldn't say that. If you take a look at the introduction, let me check if I have already captured the video. Yes, this should be fine. Okay, so if you have taken a look at the lecture, you will see that there are quite a few slides there because uh, instead of just overview on the course, I also include some of the contents into this, particularly the contents about computer sound systems, which we will not cover those in this course. So what does that mean? It means that even I'm really into the recording and audio equipment like the preamp, microphone, amplifier, and others. But we will not cover them in this course. This course is about spoken language processing or speech processing. So what we will cover will be focused on the speech, how people speak and how can we capture those and process using computer. So with those, you can create a systems that allow you to, let's say, recognize speech or synthesize speech with those. And there are even I saw I think it just the papers came up just a few months ago that they used the voice data to evaluate whether the patients have which conditions or the disease of the disease, and then they use those to evaluate maybe the stages of COVID infection, for example. So that is one of the fun things about this is that you can process human speech and then make use of those to perform different tasks. And that is what we are going to take a look at in this course, right? So in this lecture, I'm going to briefly overview the equipments, right? But if you have questions, you can ask, right? I'm actually waiting for the upgrade of this microphone. This microphone is all right, but it's well still USB interface, so I'm upgrading to something that's better for this semester. Okay, so let's start. We will start with the introduction to the course. All right. So let's start with this. We have this as the permanent link that you can use to join. The course will be on every Wednesday, 6 to 9 p.m. And you can contact me via Facebook Messengers or using the email. Both are fine. And about the textbooks, actually, the lectures that I drafted here are from many books because, to tell you the truth, there are not one book that I think is good enough for covering the whole thing about speech. I have some books that I used that are about anatomy of speech production system, like what are the composition of the vocal tract and the composition of things in our mouth, the vocal apparatus. I have books that I use that related to speech synthesis. And some of them are documents that are related to speech recognition. So with all of them together comes these lectures. So I will provide those reference on each of the topics that I use. So I will list them so that you can take a look in more detail on the thing that I used here. Okay. So what will be about in this course? So in this course, what we will focus on would be these 4 topics. The first one, we will focus on the practical and the theory of speech processing. So we will take a look at the speech data, how those data came about, and how to process those data. So if you are not familiar with the signal processing, I will try to explain them, but I think you should ask as well if you are not familiar with those techniques. Okay, so we will cover about those theory in speech processing, right? Like spectrogram, formants, pitch processings, and some algorithms that are fun that we can like modify the pitch of the speech. The pitch is something, the signal that control the I would say the tune or the melody of the speech that we have here. Okay, and we will delve to 3 tasks in speech processing. The first one is speech analysis. Speech analysis is about how we can analyze the speech data, either in forms of the Prom-on spectrum or using something like pitch to measure the tone in speech. So we will take a look at different ways that we can measure speech data. And then we will focus, and then we will take a look on the 2 applications that are widely used now today. And the first one is the speech recognition, which you can probably find in your mobile phone, and you can talk to Siri, you can talk to Google Voice. The application that translates from speech data into the text is called speech recognition. We will take a look at how it works and how can we build one using the traditional technique, using deep learning technique. And the next one, we will take a look at the work that can allow you to synthesize or generate speech data. Right? This is speech synthesis. Right? So the nicknames of these 2 applications are the speech to text and the text to speech. Right? So these will be the focus of the course. So what we will learn when we translated them into the individual topics, we will learn about acoustics of sounds. We will learn about how sounds can be represented, how can we analyze sounds. We will learn about digital speech processing, on how can we deal with the spectral and temporal domain in speech. Because when we are dealing with speech, we are dealing with both spectrum, with both the frequency domain and also with those in time domains, right? If you are, if you remember back then, maybe in the calculus courses, you may learn things about Fourier transform. Right? Fourier transform is a nice tool that allows you to transform data from the time domain to frequency domain. The direct application is to use those techniques to analyze the, I would say, the time varying data, like speech data here. Okay, and we will take a look at the things that are not really computational about the speech production and perception mechanisms. We will look at how we pronounce the sounds, how does this relate to breathing, and how do we control them to the biomechanical systems in our body. And then, we will jump to another discipline that is required in order to do things about speech processing, which is the phonetics. You need to learn about language a bit in order to understand the representation in speech. So we will learn about basic phonetics on how can we represent sounds as symbols, and how do those phoneticians use the linguistics description to analyze, to study language. And then, well, as an engineer, then it comes to the applications, right? Speech recognition and the speech synthesis. Right? These are the topics that we will cover. Now, the thing that will be related to your grade here. So this course will have basically there will be no term project, cause but there will be, say, mini projects, 4 of them. Well, you can think of them as assignments. It will be just like a few lines of code that you need to write to analyze the data. Some of them will be asking you to perform experiment and creating your own like synthesis systems, basic synthesis system. Okay, so what we will do is to, you have 4 assignments. The first one is about speech analysis, which you need to write a program to analyze speech. And then the pitch modification. With this, you have to extract the pitch out of the speech and then modify them and insert them back. Right. So for speech analysis, I would let you use the library, because that would be easier, especially in performing the fast Fourier transform and the short time Fourier transform. There is the library in Python that allows you to do that. For pitch modification, though, you have to write the code yourself after extracting the speech data. And then you need to write the code to extract the pitch out. It's not that difficult. And then you need to write a code to do the thing that is called Pisola algorithm to insert the pitch back and then modify them. Right? You can modify the word like ma into, say, ma, right? So that's possible here. And then the two tasks, the speech recognition and the speech synthesis, which I'll ask you to create the speech recognition system. Not from scratch, don't worry. Right? We will use the library to do the job, but you need to know the context in order to be able to create those. And for speech synthesis, I will ask you to prepare your own data. That will be more fun, right? To create a synthesis system using the basic, maybe concatenative synthesis. So these will be the assignments. The examination, right, there will be midterm and final examinations for both of these. And then 30% for each of these. Okay, assignment, because this, I opened this, admittedly, I opened this course for the master level students. I don't think I opened the speech processing course for undergrad for quite some time, 4 years, 3 years, I don't know, I don't remember. Right, so the assignment will be individual. However, as I saw that there are quite a number of you guys, probably almost 20 of undergrad students. Well, individual is okay, right? Do you have any objection on the individual work? No? No? No, good. Yeah, the work will be individual work, and so that just for assignments, think of them as big homework to do that. Usually you get about 3 weeks for each of the assignments to do the job, and then just submit it before the deadline. Right? And so the assignment will be about building things for speech analysis, modification, recognition, synthesis. And the software and the speech data will be provided, although some of them I will ask you to record the data, especially for the speech synthesis. That will be more fun. For recognition, I will prepare the data for you guys to train the model. Okay, and what you need to do for each of the assignments to write the report to explain what you did. I will have the template for you to work on that. Don't worry about this. Okay, next is the policies on the courses. Actually, these apply to all my courses, but I have not included this slide to my course for quite some time. So if there are academic misconducts, then the score of that will be set to 0, right? If there are certain plagiarism, that kind you copy the work from authors that I explicitly see that, and that results in 0 score, right? And the late assignment will be deducted 25% as penalty, so don't be late, right? We will use LEB2 as the main medium for assignment submission. Okay, and these are the schedules, right? I'm excited to show you this. I have modified this every time that I teach this course. For one thing, I want this to be a good experience with you guys, and also I think some of the topic need to be changed, particularly the one that I include in this semester is these two. There are these two. The first one is the speech recognition using deep learning, which is quite a trend right now. That you can use the deep learning model to perform speech recognition to identify the word from the speech data. And instead of using the classical machine learning, which in speech recognition back then in 1990 to 2005, most of the work are done by hidden Markov model. And later the CRF, the conditional random field. But lately it has been the combination of the state-based model like hidden Markov models and the deep learning models in order to use these to extract the features. So this is quite a trend, so I included here as well for your study here. So in this lecture, I will cover a lot of research papers that has been published in the past 5 years about speech recognition, and also the state-of-the-art system that has been used right now by Google, by Nuance, the company that work on, I would say the company that is behind the Siri in the early version. But for the latter version, I'm not sure. And for the speech synthesis, which we will take a look at actually my current research with the University College London and University of Cambridge. And I don't remember the university is Karlsruhe or Dresden Technical University, and that's the this is like three four university collaboration between UK, Germany and Thailand. Right? We have research collaboration on the high quality model-based speech synthesis. All right, so we will talk about that here and how you can create a simulation model that simulate the resonance of the speech in your mouth in order to produce sounds. And this is quite fascinating, especially in the degree of freedom in the control of the model to produce sound. Right, and that is what we will take a look here. Right, on the model-based speech, model-based simulation. For the generative model, it is not actually new. The current systems in speech synthesis, the high-quality system, relies on deep learning combining with the classical hidden mark, the classical state-based model to generate speech data. And it's okay to a certain extent, as you may have seen in something like I don't remember. It's Google Duo, right? Like in those demonstrations. Well, we'll take a look at the model here, right? And the underlying model on how does it work, the generative model, and how does that concept can be applied to synthesize the speech data, right? So this will be about application, and before the midterm, what we will cover are about the fundamental of speech processing. This is not audio processing though. Well, what is the difference, right? Audio processing would concerns audio acoustic processing would be about how can you reduce the noise, how can you record the data, reduce the something like reverberation, or doing signal processing with acoustic data. But we will not cover those things here. What we will cover is how to treat the speech signal. Starting with this lecture, we will take a look at the basic acoustics of sound. Right? How can we represent sounds as a signal in a computer? Right? How can we import those sounds, and what are actually the data that represent those sounds? We'll take a look at them today. And this next lecture will be about the speech production and perception. Right? By speech production, I mean how does it work when you speak? Right? The air from the lung passing through lots of things and generate sounds. How does that work? And also about perception. How do you hear the sounds? Right? The sounds come from, well, you may have learned that in physics, right? From the vibration, and then those vibration traverse through air and then hit your eardrum. We will take a look at those in the speech production and perception, understanding the speech signal. And then afterward, we will learn about spectrogram and formats. Okay, there's a question here. If I would like to learn audio processing, what are the sources you recommended to learn on this? Well, audio processing, you mean something like recording, signals to noise ratio? Well, I would suggest that you start with, is this for creative purpose or professional purpose? If it's for creative purpose, I would suggest that you can take online courses on audio processing. It would cover something like different equipments like the mic, the preamp. Mostly those are about music though, because people in the audio engineering, audio processing are those that kind of trying to get the best representation of sounds out, just like when people work in photography, right, trying to get the best light. This is like trying to get the best signal out of the recording and then mixing them using something like equalization. So, Kiribat, if I were to advise you here, I would suggest that you learn about basic signal processing. Right? Basic signal processing is the key to understand those concepts. Once you understand basic signal processing, like convolution, those that I think the third year CPE, right, on the regular program, learn the linear system and signal processing. Right? If you when you learn about those, when you understand the concept of time domain, frequency domains, and then you can find books about audio processing, about audio data. Right? Those are for professional though. But for creative purpose, I would just suggest that you take online course. That's quite enough. Right? It would just tell you about different equipments and how to do recording, what is sampling rate, and those things. But those courses will not delve into the underlying things. If you want to create the IoT that processes speech data, those online courses are not enough. You need books, you need basic foundation in signal processing. All right. So that's the thing. This course will cover that a bit though, right? We will talk about spectrum in the speech signal here, and then afterward we will then extend it further to spectro-temporal. Spectral means spectrum, frequency domain, and temporal means time domain. Combine them, you get the spectrogram. Right? When you want to analyze the data that change by time. Right? Spectrogram is very useful because it allows you to analyze frequency data on different time windows. And then extracting the data further from that, we're extracting the harmonic frequency out of the spectrum we get for Max, which is a good representation of the sound that we hear. Like when I pronounce the word R and E, these two words, the sounds that you hear, actually have different frequency content. And formanx would be the indicator that allow you to detecting those different representation of words, right? Then we will take a look at another representation of sounds, which is the pitch, right? The pitch is the, I would say the pitch is the fundamental frequencies of the sounds. Fundamental frequencies means the main vibration before the harmonic frequency. So controlling a pitch allows us to control the intonation. Like when you hear some of the, I don't know how to say some of the guys that speak English in the flat tone, that means the pitch is quite flat. For a language like Thai, we have variation in pitch. Thai, Chinese, we have tones. Tones has the variation in pitch, like when we speak ma, 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 we actually control the pitch. And when you hear the musical sounds like do, re, mi, fa, sol, la, ti, those are also the pitch, right? And we will talk about how can we extract pitch out of the speech sound. This, in order to understand this, you need to understand the fundamental of the speech production. On how does speech come from the lung, pass through the vocal fold, pass through the vocal tract, and then radiate through the lips. And then we can deconvolute the signal back into understanding what happened at the vibration level here. Right? So that will be pitch extraction. And also performing modification of the pitch. We can insert the pitch back, modifying them a bit, and then insert them back, so that we'll get a natural sounding with minimal adjustment. Or you can think about having the neutral speech, like people saying R, and then you insert a pitch so that it becomes R or become R, like that, by inserting the pitch into the sounds, right? Modifying them through the algorithm. We'll take a look at that on the fourth lectures. And then number 5 is phonetics. Although I rather it's for computer engineering, but basic phonetics. Phonetics is actually a discipline in language study. So what I will call will be the basic phonetics. So you will probably understand what does it mean by phonetic symbols, and how can you divide the sound into smaller representation like syllable, like the phonemes, right? And we'll take a look at different composition of the phonetics, particularly for Thai language here. And the last part is the before the midterm is the intonation and prosody. This is actually my research. My research area is on speech synthesis and speech prosody. So here we will take a look at the prosody and intonation, that when we speak naturally, there are information that we encode into speech that are supra-segmental, that are something that are not in words. Like, although there are words, there are something, say, a picture words than 1,000 words, now we have something that is beyond words, that is not a picture. Like when you're trying to convey emotion, you're trying to convey expression, or something that is very basic, like when you want to just raise the topics, when you just want to focus on some of the particular word. And that when intonation come by. When a child learn language since childhood, that child will have an ability to pronounce the word with intonation in English, right? With intonation, and he or she can perceive the intonation, that is this is the expression that is supposed to be, right? But as for me, as a second language learner, right, I learned English as second language. Intonation is something that you need to practice, and it kind of becoming normal once you have been around with these types of things for quite some time. So I have become familiar with the way to speak with intonation, or way to listen to intonation, just when I work abroad. Before that, no. So this is quite a thing that that people have to understand, especially for us second language learner. But for Thai doesn't have intonation, does it? But it has certain expression that you can incorporate into speaking. Right? You may have seen that in the dramas on the TV, right? When the actor want to express certain a certain emotion, they will use certain types of speech intonation to convey that. So that is about intonation and prosody. We will cover that. This is quite a fun topic here. And it is used in communication as well, particularly in English. When you have question intonation, you need to raise at the end, right? And certain word will be have certain patterns. When you have statement intonation or descriptive intonation, it will be like downward intonation. So that is the things about intonation and other topics here. Right. So these are the 12 topics that we will cover in this semester for this course. The first assignment will be out about this week. Second assignment about this week. Yeah, about this week. And then you have about 3 weeks. And then the third assignment about here. And the last assignment about here. Okay. So what are the applications related to speech processing that that you may work with if you learn this course? The first one would be the voice interface. I created this lecture, I say, since 2012. It's quite some time, because I teach this course immediately after I graduated from my PhD. After I came back from UK. So let's see, should have it here. Speech processing. Yeah, I teach this course since 2011. Right? So back then, Siri is still not here. It's somewhat there a bit. So you can interact with Siri. You can interact with Google Voice, or at least calling Xbox right now. There are also other interfaces that you can talk with. You can talk with the refrigerator. You can talk with the Alexa. So there are different types of home device that allow you to control with voice. Or even the drones, the camera, so many of them, you can control them with voice, with the voice command. The voice interface as a command, the system need to recognize that this is the word that you pronounce and then translate those words into commands. So it is basically a classification system that trying to detect what this command should be classified as. A dictation system is a system that you dictate your word into the text, just like when you talk with the Google keyboard, right? With the Android or Apple keyboard, and then it will translate that into text. That is, back then, is called dictation systems. The Dragon Dictation is actually quite old. It is a software by the company called Nuance. This is the European software company that work on speech data. They are the competitors with Google back then when I start working on the speech research. Now today, Nuance is actually the backbone of Siri. So they should be fine, still be fine there. My senior project back in 2002, my senior project on my fourth year as an undergrad student is to create the speech keyboard, right, to recognize the speech sounds and then translate that into word, Thai phoneme. Right? Back then it's Thai phoneme, just whether this is go, call, like that. But well, with the Google system right now, it's quite sufficient for it to be used in the practical application. The reason is that Google gather lots of speech data, and by using the data-driven approach, it can create systems that can recognize more of the speaker-independent manner. Right? In a year of like 2000 to I would say 1995 to 2005, people try to create a system that can work in the speaker independent manner. That is, you create a system and then anyone can use those system. It is quite hard back then, because if we use the general speech recognition model based on the basic machine learning, you need to have a lot of them, a lot of the data to represent the variations of the speaker, and that is quite hard. But with Google, with therefore to gather the data from all around the world, they can create the systems that can recognize the word quite effectively there, right? And that system use a bit of the word that we pronounce, and also the sequential dependency. Like when you pronounce the word "mẹ nám," right? It actually recognized "mẹ," and then for "nám," it used something like the dependency between the words to predict that this should be the next word. That's why when it is wrong, it wrong quite catastrophically. it is quite bad when it is not working. And application for this course, another one is the text-to-speech. Text-to-speech is not the new things. Actually, this has been researched for quite a while. There are those format synthesizer that has been done in 1970. Although it can pronounce the word that is not quite clear comparing to now. And for now there are different systems that work here. Let me click on the link. Oh, it has been removed already. This is from the Edinburgh. Never mind. So speech, the text-to-speech, right? Translating from text and then produce the speech. The core mechanisms of the thing that you see in the Siri. Although for Siri, it's more of the, I would say, template based, that it has a template and then it pronounces based on the template, only modify things that it is required, not quite interactive or composing from scratch. in speech coding, as particularly used in communication like what we are doing right now, speech has to be compressed and then code through digital channels so that it can be effectively communicated. You can use speech to do emotion recognition, or for call center to do the monitoring of emotion. And I think there is a project between the telecom company and the university right now that are trying to create a model about speech and emotion. Right? One of my colleagues here also worked on this emotion recognition or emotion representation model of speech, because if you can monitor the state of mind of the speakers, then you can create a system to detect if that speaker is angry right now, or what types of moods that that customers or that speaker has. Okay, the link you can see, you can take a look at later. This is actually the emotion database on the that has been used, that has been synthesized using speech. And this will be important as well if you want to create an agent, a computational agent or an AI that can pronounce emotion. Well, the thing that you see in Jarvis is actually recorded speech from actual human. So, well, that's for movies. If you want computer to generate emotion, then that computer has to have certain representation of emotion to convey it out. So this it is still in research right now on what types of encoding there should be, or what types of representation or modification to the speech that should be in order to convey those emotions. And not just speech, particularly it has to be face, has to be other outlet as well. Language learning software is another thing that is important back then. When I start teaching speech processing, I was hired by the language learning company in China back in 2013 to provide consultant, because they want to create a software so that other people can learn Chinese. You may wonder whether I can speak Chinese. I can't. But my research is about the model that control the intonation. And my collaborator is the Chinese professor at UCL. What we created is a system that can monitor the intonation, whether it is according to the template or not, and then determine whether the learner need to change or need to adapt. So what we provide consultants on is just on the mathematical model. So you can use speech processing to do language learning software. Well, obviously robotic, because you want robot to be able to speak. I think this is the video, yes, about Asimo. Yeah, let me share Asimo video. That it has to, let me share the sound first. Share the sound. Okay. Do you hear the sounds? All right. Because I haven't used the sharing sound feature before, so I'm not sure if you hear the sounds or not. Is it okay?
Okay.
All right.
オレンジジュースをお願いします。井上さん、ミルクティーですね。岩下さん、オレンジジュースですね。西名さん、ホットコーヒーですね。
So Asimo can recognize not just the contents, but also the source of the sounds, right? That this person's order orange juice, coffee, I don't remember another one. But you can see that in order to do so, it has to be able to localize the location of the sound source, as well as separate that sound source out, and also recognize the content of the word.
それでは、 持ってまいりますので、少々お待ちください。
Right, so this is the simultaneous voice recognition by Asimo. All right, and this is you can use speech processing to create a language translator that a person speaks in one language and then it translates into another language through the speech recognition and speech synthesis. Okay. Right now, the work in machine translation, translating one text from one language to another language, is quite established. That we can use the sequence-to-sequence model to do the language translation. So by having that framework in the middle, in combination with recognition and synthesis, we are now closer to having something like universal translator that can translate language from one to another. Right, so those are applications that are out there that use speech processing to do the work. Now, let's take a look on the fundamental of the sounds, right? Before we begin further, what is sounds, right? So you should hear the sounds here, right? So by going to different places, what do you hear here? Beside my voice. Water flowing. Bird. Yeah, how do you know? How do you know that those are birds? Those are the water flow, right? You may have heard it before. You may have heard those sounds before. But there has to be a certain physical relationship of those sounds to the physical things. How about this one? How do you know that this is about the rain? How does the raining sound generated? From something passing through the air? Hit the surfaces? Yeah, so there must be sources. And also about this one. Right. They are quite common in everydays that we may have heard them. Right? Sounds is all around us. If you don't hear any sounds, then you might hear something deeper, like your blood pressure pumping. Your blood is pumping. You may have heard those sounds before when you are in the really quiet. But in our life, it is rare that we will be in the quiet situation. So just where you are, wherever you are right now, what do you hear? You may have heard my voice, right, from the mobile phone, from the computer. Maybe your computer is running the air or the air conditioning system. Your neighbors partying, the television that is still open, or your games that you are playing together with my lecture right now. So you may have heard lots of noise. Usually, true silence does not exist for us, since we actually even before we were born, right? Even before that, we hear the sounds through our mother in the womb, and you may have heard some of the saying that if you talk to the babies during pregnancies, those words are all playing the music, and then those sounds may carry through to the child inside during pregnancy. So there is no true silence. There has never been true silence for us, because there always be sounds around us. Like you may have heard, like right now I hear the air conditioning working. If not, then I would hear something like wing 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 sounds that might come from the light, come from this light, come from computer. If not, maybe my own breathing. right? Breathing in and breathing out. All the urban noise out there. Or if you are in the studio, then you start hearing yourself, like your breath, or the blood circulation, your heart pumping. When you see cute boy and cute girl, right? Your heart. Well, so you start hearing your own bodies with that. There's no true silence. So what? And this is the sounds that you hear. Acoustic is the study of the sounds and the properties of the sounds. Okay, so acoustic is actually much more than speech. A paper that I published in the journal called the Journal of Acoustical Society of America. Actually, there are lots of work that are not related to computer engineering at all in that journal. Like you may publish something about acoustic of the sonar or radar, and those are also acoustic, or the acoustic of the vibration, or the material that can block vibration. So those are about civil engineering. So it is also about acoustic. So acoustic is quite a diverse field. So for acoustic, we the fields mostly focus on the study of sound. So what is sound? If we were to represent the sound, it is actually the pressure, the vibration of the pressure through the given medium. So after this, when you see movies that people in space talk through the helmet, then you know that it is fake, because sounds cannot travel through the vacuum, right? It cannot travel through space without any medium. The reason that you hear my voice right now, because my the vibration from my mouth travel through the air to the microphone, and then it is encoded to digital signal, and then carry over to you guys, and you have speakers that also vibrate, then creating the vibration in the air, and then you perceive through the ears. So sound has to be traveled through a certain mediums, and because it has to travel from one place to another, it need to have the production source or the generation source, and the sound is generated from the vibrating object, and the mechanical energy of the vibration is transferred to the medium, like through water, through air. Like for speakers that you hear right now, it vibrates, and then the vibration transfer to the air and hit your ears. If you put something in between your speakers and yourself, that will block the vibration. Then you wouldn't hear the word. So it needs to have the vibration. Now, let me ask you this: suppose that I knock the table like this. How does it generate sounds? Where is the vibration? Can you guess? Where is the vibration that generates sounds when you knock the table? Yeah, I would say the surface vibrate, right? Not the whole, maybe not the whole desk vibrate, yeah, but the surface, right? Just like when you play guitar. When you play guitar, the reasons that guitar has to have a chamber, although you kind of hitting the string, but the vibration from the string resonate through the chamber and then produce a sound, right? So there is a vibration in the string. So you need to have a source, right, to generate the sounds, and then it needs to propagate to a certain mediums. So it means that you can communicate through, we can communicate with one another because the sounds travel through air. Now when I'm wearing mask, the sound will be a bit muffled because it has to pass through the mask. Well, it must be like that. When you speak underwater, right, you still hear things underwater, but because the water molecules is quite dense, the sound will travel through that with limitations. So that's the reason that you hear the sounds like white, messy, right? With a medium as water. When you speak through something like walls, how can you hear the sounds when I'm talking about vibration, right? The vibration, if the wall hit the wall, if the wall is quite solid, it can absorb, it can propagate the vibration. But if you have certain surface, like say the foam, to shield the voice, then it means that the sound would kind of, the vibration energy would hit the foam, and then the foam would absorb the vibration, and that make it propagate to outside with limited quantities. That's the reasons that when you go, if you have seen the studio, you see the studio will have a lot of shielding, right? A lot of shielding in order to reduce the vibration, the propagation of the sounds. And the last thing is about perceptions, that because, well, I would say spoken, the ability to speak is originated from biology. Right? We want to communicate with one another. So we also evolved to have the ability to perceive the sounds. Right? I'm not sure which one comes first, though. Maybe perceptions come first before production. For example, when you take a look at snake, a snake can perceive vibration through the skin, but it cannot like produce sounds for communication. But other organisms like elephant, monkeys, they can communicate with one another through sounds, just like human actually. So perceptions, the sound has to be perceived and interpreted. So both human ears and computers are the examples. So in physics, what is sounds, right? The sounds is known as a longitudinal pressure variation, right? If you think about the wave that traveling through space, there are two types of wave. The first one is the traversing wave and the longitudinal wave. The traversing wave is like the wave in the ocean that you see it rising up and down, right? And the longitudinal wave is the wave that conveying through space by means of condensation and rarefaction. Right? These are like the molecule of air become squeezed to one another and then expand, and then squeeze and expand. Right? This is the process of the longitudinal pressure variations, and the peak of the condensation of the molecule generates something like the high pressure in the air, and the measurement of one point to another point, we call that the period or the wavelength. And you may have learned this in physics. So pressure variation at different frequency will generate different type of sounds. I think I shared the sound. Okay, like this one. Right. You can see that because it has lower amplitude, right? And by having lower amplitude means it has more spread apart air particle in the sounds. And for this one, when it is condensed, you can see, you can hear it quite clearly. So sound carrying through space by the pressure in the air, right? So comparing to the transverse wave, longitudinal wave traveling in the same direction of the propagation. Like when you play with a spring, well, it will go into like, well, I actually have that spring here. My sons play with that when he's a kid. I can show you that. But actually, if we are not in the social distancing mode, I will ask you guys to just line up and then play with people to show you how the traversing wave is done. But because we cannot do that, so I find this out, right? I actually have the animation afterward. Right, maybe let's jump to that first. Here. This is how the wave is traveling to the space by means of condensation and rarefaction. Think about traffic jam in Bangkok, just like that, right? When it kind of is kind of just like the traffic jam, that the phenomenon it going into this direction and it slow down, and when it become dense, it kind of creating a pressure, and then it release out. So this is the longitudinal wave, right? So the particles stay about the same, but the wave traveling through space. Okay, and because of this, the wave of air can really be, I would say the particle in air can really be traverse. The wave cannot be traverse. Traverse means up and down. It can be kind of pulling together or pulling apart. And the reason that it bump together because there are certain molecules that tie the air together. Right? So you can play with this in the crowded line. Like if you push your friend, the wave of pushing friends will kind of propagate to the line, right, to the front. Okay, so this is how the sound travels through space. Okay, now if we measure the properties of the sounds, measure the condensation, measure the pressure variation there, right, we will have this height as the amplitude, which represents the pressure in the variation, and one period of vibration, we call that the wavelength, and the inverse of the wavelength, we call it the frequency. Right? Frequency refer to how many cycle, how many periods happens within 1 second. Okay, the frequency units is hertz, which refer to the cycle per second. The relationship with the time domain is that the period is 1 over frequency, and vice versa, frequency is 1 over period. Okay, so this is the properties of the wave in physics that you may have learned before. Now, so it means that in physical world, right, sound is the vibration of the air. And how can that be translated or captured by computer? You may answer, obviously, microphone, right? It must be converted to microphone. But how does that work? Let's take a look. Right, so the speech sound is actually an analog signal. And this analog signal has to be captured by the microphone, and the signal from the microphone as an analog signal has to go through the analog to digital converter. Right, so this is the input speech sound through microphone, and then passing through analog to digital converter, and you have the computer signal, digital signal, and with the processing, like the DSP processing program, it can be processed and then produce sounds out to the digital to analog converter, right, and then produce the output speech sounds as an analog signal. So this is the paradigm in, I would say, audio processing, not just speech processing. Like if you are into music, then you may already have something like the preamp or the amp, which can convert the analog data from, say, microphone, or maybe from the electric guitar, to digitize them and then store them, and then passing through some type of plug-in DSP processing, generating the sound, and then producing it to speakers. Right. So this is the kind of the thing. When we talk about speech, it's also the same thing, that we have speech sound coming in. This speech sound is represented as the digital data. Processing may be recognized as what type of text it is, and then used in the program to determine the action need to be done. And maybe that action will be produce another sound. So the program generates another sound and then produce it to the speaker, to the digital to analog converter. Okay, let's take a look at different components here. The ADC, analog to digital converter. The purpose of analog to digital converter is a device that converts analog signal to discrete or digital signal. ADC has to perform two tasks, right? except the amplification, because some microphone require amplification. For example, the microphone that I'm using here is called a condenser microphone. You need to have power to power the diaphragm so that it can receive the variation in the pressure, and then translate that into the signal, and then those signal will be passed through amplifier and then to the ADC, to the analog to digital converter. This analog to digital converter will perform two tasks: sampling and quantization. Okay. This is in the X5 Fatality Pro Sound Card, the one that is quite new when I creating this slide. But right now, well, there are a lot better audio interface out there. So the process, two process. The first one is sampling. Right? From analog signal, how do you sample the data out? In theory, right, sampling is done by taking sample just one point far apart of one another. Right? So mathematically, you can think about having a number of impulse. You remember the impulse in calculus 3, I think. Calculus 3 linear algebra. You can have impulse and then convolute this impulse with the audio signal, with the speech signal. That's mathematical term. But in reality, what you want is to take one sample of data here and then take another sample here, take another sample here, so that you have something like the X4 here, X4NT, that you have the value of data in the uniform interval. This is called the uniform sampling. That is, you are sampling the data with equal interval every time. How does it done in the circuit, right? Well, mathematically, it is done by having the impulse train. This is impulse. Do you remember? Have you seen this symbol before? Delta here. Right? It's called impulse. The property of impulse, if you don't remember, is that if you integrate the impulse, you get the value of 1. Right? If the impulse will have the amplitude of infinity at 0, right, at the point 0, and 0 elsewhere. So it represents the event that occur at one moment. So here, the impulse trains means that we have this delta t minus nt, which represent a train of impulse that are t apart. If we have n equal like 0, 1, 2, 3, 1 delta means one arrow here, and we combine a number of them together. Then we have a train of impulse, this pt. Pt would have the thing that is called the period. We call this a sampling period, which is the space, or I would say the time between the two peaks here. This is called sampling period. This is an inverse proportional to the sampling frequency that we set in the audio interface. Right? Like for the recording, you may use like 44K, 48K, which means that 1 second you have 48 samples, right? So that will be inverse proportional to, so the period will be inverse proportional to that frequency. This is sampling period, okay? And the fundamental frequency in the angular term is omega s equal to pi over t here. In the frequency normal frequency domain, it will be just 1 over t. Right? This is like this is the fundamental frequency related to the frequency of the sounds. Right? When writing is like this, is in the what we call is the angular frequency. If I were to use the fs, normal fs, this will be equals 1 over t. Okay. All right. Right. So mathematically, sampling is the process of having impulse train like this one, and then we perform we perform multiplication of the impulse train with the actual signal. When you perform the two signals together, the one that is multiplied by this location would be represented by just the data above here. So this is a mathematical representation of sampling, right? By multiplying the two signal, the xt, which is analog signal, and pt, which is impulse train. What you get here is the value of x and t at specific time point. Yeah, but in reality, we are not doing that. That is mathematical operation in the ideal situation. In reality, we need to create a system that able to sample the data, and that is a basic circuit that can do the job. That circuit is called the sample and hold circuit. Sample and hold circuit will sample the data at one point in time and then keep it fixed until it reach another time point, and then it will sample again. So we have the next value. So this is the process of sample and hold. Just like this IC, the analog device AD585, which can perform sample and hold amplifier. Right, so I'm not going to go into detail here, but it will perform sample and hold just like this one. What does it mean by sample and hold? It will actually sample the data and then hold the value until it reach the next time point that it need to sample again, and then hold the value, right? And then sample again, hold the value. So this is how it works in the actual IC that perform sampling. That's why we have this digital signal out of the analog signal. So this is the first step, sampling. Okay, so what does it mean by having higher sampling rate? Right, can you tell me what would happen if we were to increase the sampling rate, the number of points to sample and hold for this signal? What will happen? We will have, well, you can answer in Thai because some of you guys are from Thai section. We will have more accurate analog, smoother, yeah, and closer to original. That's true. Right? That's why actually the audio interface right now can sampling up to 192 kilohertz, right? For well, I don't know why you need that level of sampling though. 48K is more than enough. Well, 192 points, not 192,000 points per 1 second. Imagine, right? Human speech range is only to about 20 to 20K hertz. Right? Most of our speech occupy that region. Well, but admittedly, some of the sounds, like from musical instrument, may occupy higher frequency range. So it might be having to related to those applications. Right? So you have a closer representation, right? and higher quality of the speech. Okay. So what is the sufficient level of the sampling frequency? That is a theorem that said that for a uniform sampling rate, Fs, the highest frequency for an unambiguously representation is Fs over 2, right? Fs over 2 is called the Nyquist frequency. So what does that mean? It means that for the CD players, for CD player use the sampling frequency of 44.1 kilohertz, 44.1 sample per second. It means that CD has Nyquist frequency of 22.05 kilohertz. That means CD sampling through CD can represent the maximum frequency of 22K. About that. Right, the frequency beyond 22K cannot be accurately represented. If we are not filtering them out, it will create something like aliasing effect, that some of the high frequency will fall back and then creating some type of noise in the sounds. So sampling frequency will relate to the maximum frequency that you want to record. If you have not if you're sampling with not enough sampling frequency, you will create certain effects called aliasing. Right? Aliasing is the effect that caused that cause the signal to become indistinguishable between the high frequency and the low frequency. How does that happen? It happens by having not enough Nyquist frequency. And for example, you use the CD recording frequency, and the data that is beyond 22K, if you are not properly filtering them out, those data will be I would say, fallback. And then being recorded at the lower frequency, and then it creates a types of a noise. You may have seen this in something like if you take a look at my video right now, you may see some types of stripes being weird. That is also aliasing in pictures, right? So aliasing occurs when the system cannot handle high frequency content in the data, like this one. You can see that the data we have there, the red lines have high frequency, but if we sample it with lower frequency here, it creates a types of blue line here that is not actually the actual data, right? It is distorted from the actual data. This is aliasing effect, right? How does it work in aliasing effect? Yeah, I think this is quite problematic. So we have some of you from the Thai section, right? And some of you from the international sections. The Thai section would have probably seen this graph before. Am I right? In the signal and system. Or actually, if I remember correctly, you should have seen this graph in Calculus 3. Yeah, in signal. But in Calculus 3, I remember that you also learned about Fourier transform and writing the xj omega, the frequency content, the magnitude of the Fourier transform and the Fourier series. It is actually this one. So this graph represents the signal in frequency domain. It means that if you were to represent the data like this one, like this signal, in the frequency domain, or your voice in the frequency domain, if you occupy the frequency range at maximum of omega m, and minus omega m here. Minus omega m comes from the properties of Fourier transform, that it has symmetric in the plus frequency and minus frequency. But actually, if you take a look at just the real part, the plus frequency is like your data will occupy the low part of the frequency, right? From the lower vibration to the higher part, to a certain point. For human speech is 20 to 20k hertz here. So think about this as 20k hertz. So we can represent the speech in time domain as this graph, like this triangle, right? Occupying a certain region of maximum frequency. If we sampling the data, if we were to sampling the data by multiplying the impulse train to the xt, the representation of multiplication here in calculus would result in, you remember, xt, this is from calculus, x3 convolute with x omega. Sorry, let me erase this and write a new one. This would equal x omega convolute with p omega. So multiplication in time domain is actually the convolution. In Thai is ผลการประสาน in frequency domain. Convolution is like you are putting the two signal and then merging them together. So for this one, when you have multiple impulse and one signal model like this one, convolution between x omega and p omega will result in the shifted version of this triangle to occupy different part of the frequency here of omega s here. Now, if you have enough omega s, if omega s is high enough, omega s is here, if it is like far apart enough, it means that frequency content of your data would not be overlapped. That means you can represent the whole thing of the data that is there. There's no distortion if omega s is more than 2 omega m, because this is omega m, more than 2 omega m, omega s here. It means that the frequency would not be overlapped. But if it is not, if omega s is less than 2 omega m, there will be a certain folding back of the high frequency content that would create something like this one. And you can see that the shape itself is not like the above. The above is like you have multiple versions of the triangle, and when creating this through the speakers, like you just producing this version out, just this version out, so it's fine. But if you have the omega s less than omega m, it means that there will be a certain mixing between high frequency content, and that's the problematic part, the aliasing part. The aliasing part that occurs because the Nyquist frequency. This lecture is not about speech processing yet, though. Just to outline acoustic, but the rest of the course is not about this topic at all. Okay, although we'll touch some of the concept on frequency domain, we will not directly use them like this lecture. Right? This lecture I just kind of outline the acoustic of sound so that you see what sound is first, how does it work with computer, before going to the actual speech production that comes from the lung, comes from vocal fold, the vibration. All right. So in the real world, the theory of Fourier transform say that you can represent the sounds with the combination of sinusoidal, right? So the sounds, all sound can be expressed as a combination of the sinusoidals. So it is a sine and the angular frequency T and the phase, okay? And H here is the harmonic frequency on which harmonic that you talk about. So if we talk about a certain key on piano, right? C8 on piano is 4186 hertz, but the sixth harmonic of C8, when you play piano or when you play guitar or when you play any musical instrument, you may have observed that those instruments contains chambers. It will contain empty space. For guitar, you have a chamber. For acoustic guitar, not for electrical guitar, that's different things, right? For the drum, well, you need to have a certain space for the drum to vibrate. Right? For flute, saxophones, you need to have certain chamber for resonance to occur, to create harmonic frequency. And different devices, different musical instrument will result in different harmonic frequencies content. So if on the base level, C8 has the fundamental frequency of 4000 hertz, the sixth harmonic is 25, is much more than 20 kHz, right? So it's much more than the Nyquist frequency of the CD. That's why there is the A to D device right now can record up to like 192,000 hertz, right? So maybe for this recording. Okay. So in order to avoid that, when you record in lower frequency, you need to have this anti-aliasing filters before sample and hold. This anti-aliasing filter is usually not a digital device. It is an analog device built into the amplifier, built into the A to D, before the A to D. So it's there. right? That limit the that kind of taking care of the aliasing effect that may occur when you're recording at a certain sampling frequency. So what it does is to this would create types of low pass filter. This low pass filter will allow the data that have frequency below the maximum, below the Nyquist frequency, right? Below the Nyquist frequency to pass through. Anything that is higher than that will be disregarded. That's why when you have A to D, right, the analog to digital converter, it would not create an aliasing effect because there is an aliasing filter to remove the high frequency content out before it record. Okay, so this is analog filter, right? When we talk about filtering, right, the concept of filtering is to modify the amplitude of different frequencies, right? You can understand filtering by looking at the frequency response of the filter. I'm not sure if you remember this. Most of the contents here are in either signal systems or in the calculus tree, right? When you learn about Laplace, Fourier transform, Laplace transform, system function, frequency response. So devices, you will have the frequency response. The filter is, you can think of it as a device that modify the data from one frequency to limit and then filter some of the frequency out. So filtering is a process of removing or modifying the signal of a certain amplitude out. So there are different types of filter. The one that I'm showing you here is called the low pass filter because it allows only the low frequency to pass, right? This is used a lot in digital communication, like back then in what is called digital communication when you transmit the data through AM, the amplitude modulation, or FM. The low pass filter is necessary to recover the part of the signal out. So it is quite incorporated in the telecommunication process. There are other filters as well, like this black line here is the flat response. Like flat response means that it will not emphasize any part of the data that's coming out, right? Of the signal that's coming out. The red line here is the high boost, the treble boost, because this, if you passing the signal through this, it will enhance the signal as 20 kHz, the high frequency. And this one is low cut filter, right? In order to remove the treble from or the bass from the sound. Why would you want to do that? In audio processing, you may want to remove the bass sound out. If like recording occurring when I speak closer to the mic, there is a proximity effect, and there will be a lot of bass in my sound. Maybe it will be the sound of the saliva in my mouth. So maybe you want to remove those out by create the low bass cut here. Actually, right now the microphone can act as some types of microphone would contain this type of filter that allow you to select on which type of frequency response you want from the microphone that it record. Right, for anti-aliasing filter, it's like the brick wall filter that allow anything that is below 20 kilohertz and then cut everything, right, that is beyond 20 kilohertz. So imagine that if you passing a signal through this filter, anything that is below 20 kilohertz would be multiplied by 1 according to the Fourier transform, right? Multiplication it's like this. Actually, you would have this xt passing through a filter and get yt. This filter would have representation of h omega. This is called frequency response. here, H omega. So think about decomposing xt into multiple sinusoidal. I say if you have signals like piano playing, you a C key, then there will be a multiple C key, a C key, first harmonic, second harmonic, and third harmonic, and so on. Right? Anything at the harmonics and the main component that is below 20 kilohertz will be multiplied with 1 according to Fourier series, Fourier transform. And then once you combine the rest back to get YT, right, you get the signal that is below 20K. This is called low pass filter. Okay, so anti-aliasing using low pass filter as the method to filter high frequency content out. Okay, so that's aliasing filter, right? So now you have seen sampling and then getting data, but it's not done yet. Next step after sample is that each sample need to be converted into digital data. And what types of conversion can be done? You can convert it into the fixed point unsigned like 8-bit, right? The current audio interface can convert up to 24-bit, right? 24-bit is like 16 million, 16 million level of the sound, right? But usually, like if we just convert it, back then it would be like 8-bit, right? For more resolution, 16-bit. So you can convert it using the two complement, having positive and negative value. Usually it would be done this way because sound would have certain vibration in the pressure, and it will be represented as the positive part and the negative part. And computer would, after that, you can like represent it as floating point. Usually this is done in the audio workbench, audio software. Represent everything as floating point. But during ADC, during the analog to digital, this will be done with the quantization. What is quantization, right? So when we have the data coming in the blue line here, after sampling, the input wave in the blue, the ADC will be in the black. And the black here, you can see that instead of taking the value at every value at every point, the value will be quantized or classified into level according to the bit. So if you have 2-bit, you would have like 4 level quantization. But for this one, it has like how many level? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 11, right? About 11 level or 12 level. And so each of these, for example, you can see here that although the input value is not there yet on the above here, but the ADC output would be about here because of the quantization level, because when you round it up, it will be the value here. And this creates a certain quantization error down here. This is the errors or the noises from sampling. This is the process of quantization. So different devices would have different bit in sampling. In 8-bit, well, 12 is the telephones. 8-bit is like wave file back then. 16 bits for CD. Right now, if you record using your own sound card in the computer, you can record up to 24 bits for recording and professional device. After recording at high level, sometimes you can reduce the data rate down. This is called subsampling or downsampling. The process of downsampling is to take sample, sample out. So for CD, like in 44 kilohertz, if you're sampling it down to 5, like 11.0 to 5 kilohertz, you kind of reducing the data rate out. So how does it done in downsampling? Well, you have this one, the data. Downsampling data is the sparse representation of the data, like if you take K every 5 point. But be careful here, because if we were to perform downsampling, it is possible that we will violate the Nyquist criterion and then generate aliasing. All right. So in order to make sure that that doesn't happen, filter has to be applied. in order to reduce the sampling rate. Right? You need to kind of, for example, if you were to convert the data from CD quality 44K to the file quality of 11K, Nyquist frequency will be 5K. It means that we need to apply the 5 kilohertz filter to filter the data first before taking sample. Okay. So that's how to avoid the noise. Right. So after everything done, we will get this one. Right. This is the results from the program called Pratt. Right. I will introduce that program to you guys later on. Pratt is the phonetics program. You can freely download it. The program allows you to display speech signal and then modify it according to the phonetics theory. And this is one I plotted using Pratt. It shows you like that this is the sounds. I think this is the word like testing. And when you take a look at the time domain of the speech data, what do you see? You see that, well, there are polarity, plus and minus. And this is the word testing. And this part, no vibration. No vibration in microphone, meaning that I didn't speak anything. That is the silent part. And this is t, a, and s, right? And test. This is a s sound. And t here, as you can see the spike, t and ing. Right? This is the word testing. And you can see that the patterns somehow also carrying through the way the variations. And what else do you see in this graph? Can you make certain observation from the graph? Do you see any type of patterns out here? Not through silence for sure, my room. How about this? You can see here, the peak seems to have equal distance, right? Either on the positive side or on the negative side, on the T. But on the S, it doesn't have patterns. Why is that? On the T, there's the spike, but there's no vibration. There's no consistent pattern. But on the ing, there are certain consistent pattern. And when when the voice kind of trailing off, you can see that it kind of trail off here as well. So there are associations between the speech signal that we pronounce and also the pattern that we see in the time domain. And this is the representation of the speech in the time domain, right? The amplitude represents the pressure. So by varying up and down, this is like the variation in pressure. Okay. When there is no pattern, means that the variation occur in random. Right. So when you record the sounds, and you may have hear the noise. Those noise are these random patterns. Okay. And time domain convert using Fourier transform. How? If you take a small window here, a very small window here, and using FFT, fast Fourier transform, this will convert a small portion of signal here into frequency domain. So you know that the spectrum content of this short period. And if you move this sound, move this window throughout the signal, it will analyze the frequency content of small part of this signal, so that you know that at this time point there are this much frequency on this specific window, and it will change according to the time point that it occurs. Like this time point, it will have at that time point, it will have the low frequency content on the T, and S, when you have S sound, you can see that without there's no black line here. You learn about those black lines later in the, I would say, in the third lecture about the formants, about the spectrogram. Right? So how does that originated from, and how to extract it out of the speech data. This is the sound, the t sound, and the ing sound here. So from the testing, this is called the time frequency domain, because in this graph, it represents both time domain that change and also the frequency content of the sounds that change. With this conversion, I actually have one of the students that currently is doing the thesis in bees. I don't think he take this course though, he already took that. He worked on the bees communication. He represent the data using this is called spectrogram, and then using deep learning to recognize the different activities of the bee to know that this is the excitation period, this is like the calming period. Right, so this is spectrogram. You learn about this more later. So it means that speech sound vary in time and varying in frequency, right? Both of them. And from the signal, oh, that's not welcome. I thought it's testing. It's actually welcome, right? So this is welcome. So from the signal, each signal actually can be encoded to word. You have well here, well, and come. Sounds also have certain properties because it is a signal. When the two sound waves are presented together, it will be superposition, adding together, and it can create the interference. And the interference can be constructive or destructive. Like if you have two similar frequency, it will produce the beat, and depending on the phase of the sounds, it may cancel one out or it may amplify another. I don't know if I have the sound here. No. Just think about when you hear the sounds from ambulance, right? If you traveling toward that ambulance, you hear the sound with a higher pitch, and that is occurring from the sound combining with itself when you're traveling to space. But when you kind of traveling out, the sound will change. And also when you add the two signals with different phase, that signals can create the interference, right, if the phase is out of phase. Right, so basically, if you add a signal with the same phase, you get the higher frequency. But if it is out of phase, then it creates interference. This is actually the basic mechanism of these things. Ta-da. The noise cancellation headphone. Right. The active noise cancellation use this property. It creates the out of phase of the noise to subtract them out of the actual noise or actual speech, actual voice data. By having a microphone, it perceives the noise and then use that noise to subtract out of the actual noise that occurs. Nowadays, you don't need to have like this bug headphone to have noise cancellation. With a small like AirPod, you can also do the noise cancellation. How can it perform that? With just a small device, right? It needs to generate the noise, but on the opposite direction, the out of phase noise, and then combine them with the sound itself. So this is the superposition of the sounds, and I think the underlying idea of the interference, and then is used in creating the noise cancellation headphone. So the sounds would need to travel through space, and it requires a certain energy to pushing the atom and the molecule of the air to distance, and that make it actually hard to travel through space. So sound is characterized by the loudness of sound is characterized by the decibel. This decibel or the sound level is actually the logarithmic comparison of the sound sound intensity to the bass intensity. Okay, so this is the log 2 of 10 log 2 of the I over I0. I0 is the threshold of the 0 decibel. Okay, so it's actually 20 log P over P0 when we use pressure as the measurement. That is like a rule of thumb in audio engineering, that suppose that I speak closer to the mic like this. If I were to move away from the mic for like twice the distance, then I will reduce the loudness by 6 decibel. A certain rule of thumb there. But never mind. We will not dealing with the sound intensity by ourselves here, because the course is about speech, human spoken sounds. Right? But this is like general acoustic. So conversational level is about 60 decibel, right? 120 is pain level. You may have exposed that if you go to the concert. 10 decibel is barely detectable, hardly in real life though here. Right, so conversation is about 60 decibel. And how do we perceive sound? Right, we perceive sound by the pressure variation would displace the membrane in our ear. You may have learned this in your primary school or high school. Right, to the eardrum, to the microphone, it displaces the membrane. Right, in the eardrum, displace the membrane, and the eardrum would be wiggle according to the frequency. Our ears can hear about 20 to 20 kHz, but different organisms would hear differently. Like dog and cat would have higher, wider perception range. A microphone also, and this microphone like this, also contains a certain membrane that vibrate when it is exposed to the pressure. So there are different type of microphone. Like this one is condenser microphone. Means that the condenser microphone required to have powering this microphone. So it means that it will generate a type of field that when the pressure vibration hit that field, the membrane would vibrate easily, have high sensitivity. There's different types of microphone called a dynamic microphone. That microphone doesn't really require power to kind of wiggle the membrane, but it can generate a very low level of output. That's why you need to have amplifier to use dynamic microphone. All right. So in speech perception, usually human would have like speech coming in, hitting the membrane, and then in the fluid inside would kind of trigger different eardrum that will wiggle according to different frequency, and the frequency is sensed through, there's a nerve that sends the vibration of the fluid in the ear here in the eardrum here to sense different types of frequency. With this, actually, scientists has trying to find a way to circumvent the problem of certain hearing difficulties by creating a hearing aid that interface directly to the eardrum here. So instead of relying on the wiggle of the eardrum to create a frequency and to hit the nerve, one of the professor that I at the UCL, the university I work on the postdoc, he worked on creating a device that the patient with disable on hearing can wear that, and then it will interface directly to the nerve, and then to the cochlea. It is called cochlear implant. So by implanting the hearing device to the cochlea, it allows the cochlear implant to transform the speech sound to the vibration to trigger the nerve directly, allowing those people to hear. Right? So this is the actually technology combining with biomedical, right, to like helping humanities there. Right. So come back to the property of sounds again. This is the equi-loudness. It's called the equi-loudness curve. We hear different loudness at different frequency. What should I say? At different frequency, we will perceive loudness differently. For example, at the low frequency, right, the low frequency, in order to perceive the loudness, right, the sound pressure level need to be high. But for the high frequency, the sound pressure doesn't need to be high to perceive at a certain loudness. Right? So comparing these sounds. Come on. How come it doesn't should show? Coming out. I did. Okay. Right. Comparing this one to this one. Hopefully you would hear that, because traveling to social distancing here, this is not guaranteed that you hear it. So the first one here, okay, it's a little bit quieter than the first one. How about this one? Which of these two has higher loudness? You may perceive that this one is maybe louder than the earlier one, right? But actually it's not that. Both have the same amplitude, but this one has higher frequency. That's why you perceive it has louder sound. Again, comparing between these two. Well, it is arguable, right? Maybe you will perceive this as louder, but it actually has lower amplitude comparing to the first one. This is the perception of the sounds. We can hear the sound ranging from 20 Hz to 20 kHz, but not in linear fashion. Okay, we perceive higher frequency as louder than the lower frequency. Okay, the louder these are the threshold of audibility, meaning that if you want to hear the sound at this frequency, you need to create a high pressure variation. That's why if you want to hear something like the bass and the drum, it kind of propagating through your body at the low frequency. Comparing to hearing sounds from guitar, the sound from high frequency instruments, for those you hear it like without any effort, right? When you just let's say when you can just hit the bell and then you hear the high frequency sound quite clear. But for the low frequency sound to be clear, need to have high energy. That's why the subwoofer that create the bass sound, we need a lot of power there, right? Comparing to just having like two headphones without a subwoofer, it doesn't really require power to generate those much. All right. Another concepts which is not covered in the course, though is really cool concept in sounds: localization of sounds. You can localize the sound because we human actually detect the location of sound differently. I'm talking about human though, because if we talk about different organism would perceive localization differently. Like the bat would perceive things differently. A snake would perceive through the skins. As human, we have two ears, so we detect we localize the sound at the low frequency through the phase difference. The difference between the phase between two ears. That one wave hit the ear before another at the low frequency. Maybe you can try that at concert next time. We have time. We have chance for that. Otherwise, you can try playing at home. If you kind of play a loud drum, then if you turn around, then you can hear that you can hear the sound from one before the other. So that's how it is done in the low frequency content. In high frequency content, because it is quite high frequency, we detect the relative intensity in both, and usually this is the normal method that when we create a robot, we would implement the robot by, if we have like two microphones, we will detect the relative intensity of the sounds coming between both microphones, and then we will know which direction that the robot need to turn to say the sound source come from this location. Localization. And going out, speaker, this is like the inverse eardrum because it vibrates. For the eardrum, from the vibration coming in, the eardrum has to vibrate, wiggle, and then the liquid in the eardrum, in the cochlea, will resonate, will vibrate according to the frequency, and the hair, the sensors, would sensor those out. For speakers, the membrane would vibrate according to the pressure into the data, and pushing out to create compression, pulling back to create the rarefaction, and that's how the speaker creates sounds. So it must execute quite complex motion. Well, I think speakers right now like to show off. You take a look at the speakers at the department store, you can see that the speaker you can actually see the vibration at the speaker. And then if you observe that vibration, you'll see that at low frequency it's quite obvious. At high frequency, another thing, right? This is visible. And because of this is like speaker going out, another types of sounds going out also comes from musical instrument. When you have different musical instruments generating sounds, the sounds coming out may look differently. If, for example, if you knock the sound fork, you get a pure sinusoidal like this one. The soft piano also generate quite pure sinusoidal. For the loud piano, well, you now generate some type of distortion here. The trumpet and the horn, the violin, human also have this type of repetitive pattern, which we will see on the next lecture. We'll take a look at how, if we were to zoom in into those graphs, we'll see similar structure. The repetitive structure here, that actually occur from the vibration at the vocal fold. We'll take a look at the vocal fold, right, in the picture though, and how it works in the video. The reasons that you see different structure like this actually can be explained by Fourier series, because there is a combination of multiple sinusoidal, from the basic sinusoidal to the higher frequency of the sinusoidal with different amplitude. So it means that for the time series like this one, in the Fourier series, you can have just one bar, one frequency at 5K. For this one, it is actually the combination between two psi function. The first function at 5K, the second at 10K. Combine them, you get the sounds like this one. With three frequency, 5K, 10K, and 20K, you get the time domain like this one. You can see that this one is actually quite like the one down here, right? So it means that we can actually decompose the signal here into multiple sinusoidal and able to analyze them. Okay. Don't worry, I'm not going to ask you guys to work on the math to solve Fourier transform. This course is more like application course. So you need to understand the concepts, but I'm not focusing on solving equations here. In writing code, you need to deal with the data, understand the concept, understand algorithm. Will allow you to extract the part of that data out. When using library, you need to understand Fourier. Otherwise, you wouldn't know that the representation there is actually the spectrum. And or if you use the tool like Pratt, which not engineering use though, it's phonetician, those from the language domain. It means that they don't know anything about writing program at all. Right? So don't worry about a lot of mathematical representation here. If people in language department can work on this, you can as well. But well, that is a concept here in mathematics, that when you combine multiple sinusoidal, you get the structure that is close to what I represent there. If we talk about the square wave is actually the combination of the infinite number of the frequency component, right? So there are certain trade-off between sinusoidal and the square, because if you want to represent the perfect square, you need infinite number of sides to do that. So this is called the harmonic frequency. Harmonic frequency occurs from the resonance, right? You need to have a chamber, right, in or cavity in order to create resonance. You need to have main vibration going to resonance, and then once the sound that resonate from those vibration go out, it will create different sounds, like in ukulele, in guitar, in human speech. Right, so that's all for the introduction. Mostly what I cover today is about acoustics, about how sounds generate. The course, though, will not be about how those will not be actually about how those sounds generate, but the course will be about the production of the sounds by human vocal apparatus, and how can we write a program, or how can we use the software to process those sounds. That's the name speech processing. All right, so this is it for the introduction for today. Okay. เป็นไงบ้าง Is it all right? Okay. So for the next lectures, I will post the lecture beforehand, so that you have time. If you want, you can have time to review it before the class. Otherwise, well, you can join the class afterward. And if you cannot catch the class in time, I'm going to combine the video and upload, right? Try to keep at that to the schedule if I'm not too busy here. Okay. Any question? You can type, or you can open the mic and speak out. In Thai, it's fine. English, fine as well. Okay. It has a question about noise cancellation. So in order to work, the headphone have to generate the opposite sound wave of the noise to cancel out. But how can cancel each other, since the noise sounds may already pass through our ears before it can generate? That's a good question, right? There are, like, noise cancellation actually rely on multiple properties. One property is to analyze the current level of the noise. So instead of inversing, so what I explain is like you take the noise data and then trying to reverse polarity and add that to the actual signal. This is actually the concept that is used in the car, right? The car that can cancel the sounds of the engine out. In, I think, BMW some series, though I don't remember. So it used this property. Another way to work on that is to have the device analyzing the current noise profile. So it knows that the current noise profile should be around this frequency, and then it create a filter. When you create a filter, and then pass the data through that filter before producing it out. You may hear that it occurs at the same time, but it actually passing through processing. It's not hard to create filter. It requires very simple calculation nowadays, not like deep learning things. Speech processing is like, if you can even do that in the I would say the microprocessing. Something like BeagleBones and what is it called, Raspberry Pi right now has more computational power than computer back then, so it's more than enough to process speech data on the fly. Right? So yeah, to answer you, it can be done by reversing polarity and then add together. That's one thing. Another is to have the device analyze the noise profile and then do it on the fly, right? Creating the filter on the fly. So it's actually creating the filter all the time when you turn that on. Okay. It works like when you use Audition, when you use Audacity to record the data, and then you want to reduce the noise. The program will ask you to highlight some part of noise to get the noise profile. Once you get the noise profile, then you can remove those noise out because it will occupy a specific frequency. The same way with the I don't know if it's supposed to work like that with this the headphone. Right? Some of the headphones, though, I don't think this one use that concept. Like I think the AirPod and the others, they kind of analyze the noise profile on the fly and then creating a types of filter all the times in order to filter the noisy part out. Mostly it will occupy the high frequency. Except when you kind of travel on the plane, though. When you travel on the plane, then the noise will be a lot, but they are quite consistent. It's easy to filter out. Noise that are not easy to filter out are like the dog barking, because that is, you can argue whether that's noise or not. All right. Any other question?
Hi, teacher.
Yeah.
I have heard that when we convert the digital to analog using DAC, right? They say that the electric current can lower the performance of DAC. How is it happen? Can you explain this?
ADC or DAC?
DAC, DAC.
DAC, right? So electric current can interfere with DAC, right? That's what you are talking about. That means you are like the audiophile, like to buy headphones. Right? So DAC, what is DAC? DAC is the amplifier that some headphone, not this one though, maybe something like Bayer Dynamics headphones with a lot of impedance require to have a large, high electricity level in order to drive that headphone, right? So you need to have amplifier to drive them. Your friend asked if you have better electric current can, I don't know if I catch it correctly, whether electric current can interfere with the DAC. Yes, it can, especially if the electric current has certain interference coming with it. For example, I used to use the fan together with a speaker. When you use the fan together with the speaker, sometimes you hear the vibration in the fan through your speakers. That's because the fan relying on the magnetic induction to rotate the fan blade, and that induction sometimes bleed back into electrical current, and then go through your sound systems like that. I don't know if I answer your question though, but it can interfere with the DAC through that level. Is that right? Is that your question?
Yes.
Yeah.
Okay, I have another question.
Sure.
That as I'm an audiophile, so I have when you change the material of your wire headphone, the sound profile is changed. What is happening?
The noise profile, you mean what you hear through the headphone?
Yes, and when we use the copper wire or a gold wire, we have a different profile sound.
Yeah.
So
Yes.
how it happen?
I suppose that is because, but I don't know. I don't know. I must admit that when I use different like wiring, I don't really hear those noise profile though. Possibly, maybe because of the shielding of the line, because you are talking about the connector, right? The cable, right? The gold and the silver, whatever. Probably the shielding that is the conveyor of the signal. Why is that? Because remember, if we are talking about this one is like digital headphone. It means that the signal would passing through this and then generate here. So there is no no part that can be interfere outside. But for the analog headphone, especially for the expensive headphone, it's analog part. You need to have the DAC that convert from digital to analog. And once it converts to analog, it is prone to interference, especially if the lines are not shielded. But don't believe about USB. There's actually for those for those who play with audio interface, sometimes they say that you must have the USB, very expensive USB, but USB is digital, right? Interference in digital domain is actually recoverable, not that bad. You can it depends on data rate, I guess, right? Yeah. So any more question, particularly about the cost? Well, if you are interested in headphone, I would suggest you talk to Ajahn Rashawit, and yeah, he has lots of them. For me, you can ask me about microphone.
Thanks.
Right, any more questions? All right. Well, if there's no questions, next time we will take a look deeper into speech signal. So not just any sound, but the speech sound. We will take a look at how it is produced, how it is perceived, particularly how it is produced. Because understanding how the sound is produced through our human vocal apparatus would allow us to reverse engineering that, creating the processing of the speech by representing those processes as the mathematical part, and then write a program to deal with it consequentially. All right. So that's it for today. You have questions, post into the group, right? I will work on this. Well, you guys, if you take my course last semester, sometimes the workflow is delayed depending on the workload at that time, though, because this is the first course that I teach for this semester. So there's no workload. That means I will trying to get this done tonight. All right. Okay. Any sound can be described in mix of sine wave. I would say that the sounds can be represent, or any signal, not any sound, any signal can be represented as a combination of sinusoidals. Okay. If you wonder about my statement there, take a look at Fourier series and Fourier transform. Although sometimes it is not direct representation, it will be the approximation. You can approximate the sound with the Fourier transform, and that does allow you to modify the content and understanding the frequency response of lots of things, especially if you play with the what is called the EQ, right? The EQ, equalizer, right? Equalizer is actually the filters that you can modify the content that you want to pass through. How much difference between 48K and 96 kHz when you record the sound? This is a lot. 48K is more than enough, actually, for the vocal to get something like the podcast, studio level podcast. Actually, 48K is more than enough. More than that, I think, well, if for music, maybe. But otherwise, I don't see the point, though. Because to generate it through the interface, maybe it will allow you to capture sound with lot more vibration, but maybe we try it next time. I will record it at the different sampling rate, and then doing the A/B testing, ask you whether you can perceive that. But I bet, we'll see which of you are the actual audiophile. Like let's play that game next time. I will prepare the materials and you will see. Well, I would say that beyond 16K, you will not be able to detect the difference. But let's see if that is true next time. Okay. Any further questions? All right. So see you again next time. And we will start at 6 p.m. on every Wednesday. Except if I am stuck outside, I'll try working from home, but sometimes I have to go to meetings outside as well. If I cannot make it in time, I will try to post it beforehand. All right. So for today, have a good night. See you next time. Bye bye.